It is 6 a.m. I'm in France. Let's do science. Today, we're going to talk about hydrodynamic instabilities. But first, I'm going to start by talking about what I mean by stability. So I'm not going to talk about hydrodynamic systems yet, just like systems with moving fluid, because it's really hard. So I'm going to talk about another dynamic system that's simpler, and it's an analogy. And because stability analysis applies to any dynamic system, I should be able to get the point across easier, and then we'll go back to fluids. So the system I chose was a huge marble and a bowl and a table. So what's called the equilibrium states of this dynamic system, or states like we kind of learned last time with thermo, is a state where the system doesn't change. So it'd be where the marble just sits there. And the stability of these equilibrium states is sort of like a quality to them. And I can illustrate that here using our example. So you have the marble. If you have it sitting in the bowl and it's sitting at the bottom, you'd probably agree it just is not going to move. Yeah, because you see that every day. And then if we were to set the marble on the table, you would agree that in that case, assuming you don't push it or anything, it won't move. So that's also an equilibrium state. It's a mechanical equilibrium state. But if we were to take the marble and put it on the bowl that we flipped over, if you balanced it just right, it wouldn't move. So that would be an equilibrium state. But the stability of these three equilibrium states is totally different. And the way you'd sort of define stability would be if I were to take this marble and I were to give it just a tiny nudge, like a tiny little force, what would it do? Like, how would the state, or they call it the dynamic state, or where it's its position, its velocity, like what's it going to do? And if I were to push this marble in the bowl, you'd imagine it just sort of go around a bit, and then friction would sort of eat that energy away, and then it would sit at the bottom. So this is stable, and stable meaning that if I give it a little nudge, it'll go back to the state it started at right here, the equilibrium state it started at. Neutral would mean that if I just gave it a little nudge, it would just sort of move to a new state. Depending on where I pushed it, doesn't really go back to this state or doesn't really do anything crazy. And an unstable state is sort of, you can imagine if I balanced it just right and I gave it a little bit of a nudge, it'd go crazy. It'd fly all the way down to the bottom of the bowl, off the table, or whatever. So unstable equilibrium states tend to have pretty drastic dynamic changes when you just kind of give a small nudge. And that's what we're most interested in right now. So in fluid mechanics, it turns out that a lot of steady flows, or flows that don't involve like a change in time, they tend to be unstable. So under certain conditions, if you have just a steady flow going, and you give it like a small nudge, like a disturbance from its base flow, it'll do some crazy dynamic stuff. Stuff will move around and stuff will move in crazy ways. And it's because of the base flow being unstable. So I should mention that in fluid mechanics, it tends to be these instabilities that cause a flow to transition from what we call laminar flow, which is it's very smooth flow, like you have layers of fluid going past each other, and nothing's really crossing these layers. It's pretty a lot simpler to analyze. And then you have some small little nudge from this base flow, and then these crazy instabilities happen, and then they tend to usher in a regime of what's called turbulence, which is a problem we still don't really understand very well in physics. And fluids that are turbulent are statistical in their nature, the flows are kind of random, in those little eddies that form, and it's just generally pretty hard to pick anything out of it. You have to sort of do these averages and look at average motion. But anyway, a physical example you could think of is a candle. Like if you blow out a candle and you have the smoke rising, you can generally watch this portion. This is what would be the laminar region. It's just sort of smooth looking. And then you start to see little weird oscillations, like it starts to flick around and stuff. And this would be where instabilities are starting to take over. And then it transitions into this crazy mess of turbulence. So basically instabilities in hydrodynamics or fluid mechanics are what cause pretty flows to turn into big, messy, scary flows. I'm gonna just talk about one fluid mechanical or hydrodynamic instability, and it's called the Kelvin-Helmholtz instability. So this is the basic scenario, and by the way, there are many types of instabilities. There could be one with buoyancy forces, with other factors, or like maybe a spinning fluid that has like a centrifugal force doing things. So the scenario here is you have two fluids, and they're moving past each other. This one's generally denser, so that it sits like this, and they don't have to be going in exactly in opposite directions. They could just be going different speeds. But the point is you have sort of a continuous fluid and you have some sort of boundary between these two. So this is technically, this is at equilibrium. It's just unstable. So if you were to have this boundary stay perfectly flat, which doesn't ever happen in an experiment, they would just flow past each other like this forever. But that's not the case. So if you have any sort of disturbance, like in the marble, like you give it a little tiny nudge, no matter how small it is, and I've shown that here, then what ends up happening is these bulk flows end up sort of grabbing these bumps off of that flat surface and pulling them with them. And so you'll get sort of this guy getting pulled this way with this flow, and this guy getting pulled that way with that flow. And what ends up evolving over time is they sort of start to twirl around each other, and then you get these structures that develop called vortices, and they look crazy and they're awesome looking. And basically you keep going with this until you get to the point where the forces inside of these structures are so strong that it just like rips through these layers, and you transition from laminar flow, which this would still be laminar, to turbulent flow, like big, messy, scary flow. So that's what happens a lot, and almost any flows you see most flows you see are turbulent, and the way they got there was from transitioning from some sort of laminar flow through instabilities into turbulent, chaotic flow. Crazy.